A really good way to relate the derivative and antiderivative is looking at the velocity distance relationship. So we know that we probably should qualify and say it's more displacement, but the displacement derivative is velocity. And what we've now established is that the area under the velocity function is the change in displacement or the antiderivative function. So this velocity displacement relationship is very useful because it allows us to kind of visualize and understand what's happening between the f prime and the antiderivative f. So I've given a fairly simple, straightforward example here. So we have a velocity time graph. We have a velocity that has a constant rate of 3 meters per second. And this happens for 10 seconds. And we know just intuitively that's going to be 3 meters per second times 10 or 30 meters of displacement. And what we've now established is the fact that if I want to find the displacement, I could also say that that is exactly the same as the area that we find underneath this velocity function. Okay, so that all that area must be the same as the velocity, or sorry, as the displacement. And when we calculate this area, yeah, clearly that area is going to be a height of 3, a width of 10 seconds, or displacement of 30 meters. And in fact, because it's above the x-axis, we're just going to say that's positive. So we can generalize then that the area under the velocity time graph represents displacement, because we know that it's going to be the velocity times the change in time. And that's the same as saying the height times the width. Okay. So that's a fairly simple example because it's intuitively true. We know that 33 meters per second constantly for 10 seconds is 30 meters. But what if a person's velocity is changing? Well, if the rate is changing at a constant rate, so our rate of change or the slope of this function is constant, okay, so this velocity is increasing at a constant rate of positive 1 meters per second squared, we're going to have a velocity that looks like this. We start at 3 meters per second, and we're going to end at 8 meters per second after 5 seconds. Now, we have established that the area under the velocity function is displacement. Even when the area is not a rectangle, we can work out displacement. That's fine because we can actually work out the area under a trapezoid. Okay, so this is still a geometric area that we have a formula for. So I can say that 3 meters per second plus 5 meters, sorry, 8 meters per second divided by 2 times the change in time, which is 5 seconds. We're going to end up with an area of, it's going to be 11 divided by 2 is 5.5 times 5 is 27.5 meters of displacement. So that area works out to be 27.5. Okay, so this is the area that we're talking about in here. Now, we also related it to the antiderivative, or we're claiming that this area is equivalent to the displacement on the antiderivative function. So if we take a look at the v of t function, v of t, the v of t function, that's our derivative function. We know it's going to be 3 meters per second plus 1 meters per second every second. So it's going to be 3 plus 1t. And we're saying that this has something to do with the antiderivative. So let's anti-differentiate this. We're going to say the displacement function. Well, the derivative is 3, so we're going to end up with 3t as the antiderivative. So differentiating 3t, we get 3. Here we have 1t, it's a linear function, so to differentiate to get a linear, we must start with a quadratic. And we just need to account for that extra times 2 when we differentiate with a divide by 2 here. And we do have to be a little bit careful because there is this extra plus c that could exist and disappear when we go this way, okay? But we're going the other way around, so we just have to make sure that we account for the fact that that could possibly exist. And what we're going to do then is we're going to find the change in the displacement. And that's going to be the position at 5 seconds minus the position at 0 seconds. And we can just plug that into the function. So d at t equals 5 is going to be 3 times 5 plus 5 squared over 2. And then we do have this plus c. And then we're going to subtract. I'm just going to color code this. So we have this, that's d of 5 here. And we're going to subtract d of 0. Okay, and that's when we plug 0 into this function, we get 3 times 0 plus 0 squared over 2. And again, we have to account for the fact that this plus c is involved. But conveniently, these plus c's are going to cancel. We're just gonna get rid of that. Color code this is d of 0 is all this expression in here. And the plus c's are going to cancel. And when I actually do this calculation, the displacement calculation, I'm going to end up with 15 plus 25 over 2, or 12.5, minus, well, that all calculates to 0. So the displacement I'm going to get is 25.5 meters. And I'm doing this finding the difference in the antiderivative is 27.5 meters. The area under the curve is equal to 27.5 meters. Now, that's not a coincidence. We've kind of shown that algebraically that these are actually equivalent, that the change in the original antiderivative is the same as the area underneath the curve.